having a look at worksheet number 24, homework last night. Take a peek at the answers 1 to 12. 13, 14. 6 says 5826 Fe. So iron 58. Any issues with any of those questions? Besides number 9, which clearly there was a mistake on. If you looked at number 9 on your sheet, it said 21484 polonium goes to 21080 lead. Well, lead's not 80, lead is 82. So if we change it to what it should be, not what I said on the sheet, but what it should be, we're going to say the remaining is 4,2 alpha. Okay? 6. Any others? Yep. That's right. 10. You got 6 and 10. Any others? Going once? Going twice? All right. 6 says let's do it from scratch here, even though we've got the answer written out for us here. We've got lead 208, which has an atomic number of 82. How did I know, by the way, when I looked at question number 9 and I saw that it said 21080 lead, how did I know that that's wrong, that it should be 21082 lead? Yeah. Why does it have to be 21082 as opposed to 21080? Why can't that work? Yeah. Yeah. Lead has to be 82. If it's not 82, it isn't lead. You can have atomic number 80, whatever that is, but it's not going to be lead, right? So here we have 210 lead goes plus a blank goes to 265 108 HS. I'm not even sure what element that is. Plus a neutron. So this is not a radioactivity problem, right? This is an artificial transmutation reaction that we looked at yesterday. Still, same basic idea. We have to balance out the protons. We have to balance out the protons and neutrons. Okay, let's look at the right side. 265 plus 1 is 266. 108 plus 1 is equal to 108. All right, let's look at how that balances out. 82 plus what equals 108? 26, right? 82 plus 26 is equal to 108. 208 plus what is equal to 266? 58. So how do we find out what element that is? Look in your periodic table for the number 58. No. Look in your periodic table for the number 26. And we're going to find that that's going to be iron. Iron, which has the symbol Fe, which is Latin for ferrous, right? Which is the same base of the word in ferromagnetic, right? All right, number 10. Number 10, another one of those artificial transmutation reactions here. What was that? 9,4 beryllium plus a hydrogen nucleus that's going to go to lithium 6 plus some. All right, so balance them out. Look on the left-hand side. 4 plus 1 is equal to 5. 9 plus 1 is equal to 10. All right, on the right-hand side, 3 plus 2 is equal to 5. 6 plus 4 is equal to 10. What's that going to be? 4,2 helium. Could you say 4,2 alpha? Sure, it's the same thing, right? 4,2 alpha, 4,2 helium, exactly the same thing. Yep. No, well, yeah, I suppose you could say that, because what would happen would be there would be an intermediary step there where the hydrogen would be absorbed by the beryllium. It would, for a brief time, become something else and then decay there. So I guess you could probably say that, yeah. To be honest, when I saw this, I wasn't thinking that, but that makes sense because, as I say, there is actually a process that takes place in between there. This becomes whatever, 10, right, whatever this is, which decays into that. Yep. Oh, yeah, because a helium particle, a helium nucleus is chemically identical to an alpha particle, so both would be correct. Most likely, this would appear in a multiple choice question, right? then you should be prepared to see either one of those, 4,2 helium or 4,2 alpha. I guarantee you won't see both, okay, because they're both right. Travis? No, no, not at all. No, no. The most common laser, Travis, is what's called a helium neon laser. Okay, but it has nothing to do with the nucleus itself. In fact, just the opposite. The lasers work on principles of electron transitions, not the nucleus itself. All right, we talked yesterday a little bit about half-life. We defined it as the time that it takes statistically for 1/2 of a radioactive sample to decay. Yesterday I biked home from school. It took me about 4.5 minutes to bike home from school. I don't live very far away from school, less than 2 kilometers from school. It took me about 4.5 minutes. Most days it takes me in that range of 4.5, 5 minutes. Okay, it takes me a little bit longer to get to school because it's all uphill. So 4.5 to 5 minutes most days. Okay, if I had to make a prediction as to how long it's going to take me to bike home from school today, what would I predict? Probably 4.5 to 5 minutes, right? Okay, in that range of 4.5 to 5 minutes. Because statistically, that's how long it takes me to go home from school every day when I'm biking home from school. Now, is there something that could cause me to take longer? Sure there is. Traffic, right? If there's lots of traffic, if nobody stops for me when I'm trying to cross 32nd Street, I could be waiting there for 5 minutes. Okay, it could take me 10 minutes to get home from school. Statistically, it's going to take me about 4.5 minutes to get home from school, but it could take me longer. Statistically, 1/2 of a radioactive sample will decay in 1 half-life, but it might take longer for half of it to decay, or it might take shorter for half of it to decay. We don't really know until after it's happened. The only way I'm going to know for sure how long it's taken me to get home from school today is to look at my watch after I get home. I can make a prediction before I go, but I don't know for sure until after I get home. Radioactivity is the same way. Okay? We don't know for sure how much it's going to decay, how quickly it's going to decay until after it's already happened. But we can make some pretty good predictions based on statistics, based on how quickly it's happened in the past. The time that it takes statistically for half of the sample to decay is defined as the half-life. And that varies. Okay, it varies from a tiny fraction of a second. You might have a radioactive element where 100 grams of it, 50 grams of it decays into something else in 0.5 seconds. So it's pretty much all gone in a few seconds. But you might have another radioactive element where you have 100 grams where it hasn't decayed into 50 grams for 20,000 years or 1,000,000 years. The half-life can be in the range of thousands of years or even millions of years. Okay, it ranges. There's a huge range of different half-lives. Okay, a dramatic change in half-lives, just depending upon what element you have. Yep. Yeah. No, it would have the same half-life. So if I understand your question right, Tanner, let's say radioactive element X undergoes beta decay and becomes radioactive element Y. Okay? Radioactive element Y decays by alpha decay, produces Z. Okay? Over here, completely independent of those two, you've got radioactive element Y decaying. Would this radioactive element Y have the same half-life as this one? Is that what you're saying?
So I mean, like if you were to have radio X to Y,
yeah.
Say it goes to Y as well, but if you different process, would that still have the same half-life?
Okay. Okay, that's a different story here. So Y goes to, X goes to Y goes to Z, and then Z goes to Y. No, that wouldn't happen. Oh, okay. So let's say, I think I understand it now. Let's say P goes to Y, right? Okay. Yes, they would have the same half-life. The only thing is there, Tanner, I'm not sure that would happen. I'm not sure that you get two different reactions there going to the same element. I'm not saying that it's out of the question at all, but remember there's 2,500 different isotopes. In all likelihood, if X went to Y, well, P could go to Y as well, but they probably have a different mass number. And if they had a different mass number, all bets are off. Okay, one might have a half-life of 0.5 seconds, and the other one might be completely stable, right? Depending upon the number of neutrons in there. Okay? But if they're the same isotope, no matter how it got there, then yes, they would have the same half-life. Statistically, right? Right? Okay. It doesn't mean that they're going to decay at the same rate, but statistically they'll decay at the same rate. And we said yesterday, if we have a big enough sample size, right? If we've got millions of nuclei, well then statistics work. If we've got 2 nuclei, statistics don't always work, right? Okay. If I biked home from school once and I said took me 4.5 minutes, you had to predict what was going to happen tomorrow when I bike home from school. What would you predict? Well, maybe 4.5 minutes, but okay, on a small sample size, like one time, biking home from school one time, okay, maybe I had to wait for traffic that day. Maybe there was no traffic that day. Okay, we never really know when we have a small sample size like that. Big sample sizes, maybe I go from school 100 times. Takes me 4.5 minutes. Well, it's going to take me 4.5 minutes tomorrow. Yep. No, no, not at all. Sorry? No. All right, a couple equations. One of which you're probably going to recognize a little bit. You guys are second semester of grade 12. That means you've all taken Math 30 at this point. The first equation, going to be a little bit new, but it's an easy one. Unfortunately, it does not appear on your data sheet. Little n is equal to t over t1/2. Little n is going to stand for the number of half-lives. Not the half-life, but the number of half-lives. T is going to stand for the time that's elapsed. And t1/2 is going to be the half-life. So for instance, if the half-life of radioactive material X is 3 years, and 15 years have gone by, then how many half-lives will we have had? 5, right? T is 15, divided by t1/2 is 3, 15 divided by 3 is going to be 5. We've had 5 half-lives. Okay, does that make sense? Little n is the number of half-lives, not the half-life, not the time, but the number of half-lives that have gone by. Here's the one that may look a little familiar to you. And this one, a little bit more complicated, but it does also appear on your data sheet. You recognize that one? At least something that looks pretty much like that one. Where have you seen that before? Obviously in math class, but in what context? Population stuff, okay? Exponential growth or decay, okay? Depending upon what that base is there, okay? You've probably even done an example with half-life in math class. Okay? Although half-life probably didn't make a ton of sense to you at that point, but you've probably done the example, yeah? Yeah. Good question. Good question. Travis just said, if you have 100 grams and in one half-life it goes down to 50, would the next half-life be 100? Or sorry, be 25, or would it be 0? Which one? Who says 25? Who says 0? Okay, good. 25 is right because it's half of what you have will decay in one half-life. So half of 100 will decay in the first half-life. You're down to 50. Half of 50 will decay in the second half-life, which is 25. Good question as well. So, Travis, let's look at starting it with 100. Okay, after one half-life, sorry, 0 half-lives, we got 100. After one half-life, we've got 50. After 2 half-lives, we've got 25. After 3 half-lives, we got 12.5. That doesn't make any sense. You can't have 12.5 nuclei. Well, you can have 12.5 grams. It depends on what your units are here. The other thing you got to remember is that it's statistical. So you can have statistically 12.5 nuclei. Of course, in practice, you can't. It's either got to be 12 or 13, or it could be 27. Okay, but statistically, it's going to be 12.5. Okay. After 4 half-lives, you're going to be down to 6.25, and so on and so on and so on. Your question was, can you ever get down to 0? Well, the answer is statistically no, because you keep dividing by 2, and it keeps getting a smaller and smaller number that gets infinitely close to 0. Right? What's that called? Yeah. Gets infinitely close to zero, but it never actually gets to zero. Now, in practice, what happens? Well, when you're down to one nucleus, it either decays or doesn't. So at some point, okay, it could be millions and millions of years, or it could be 5 minutes, depending upon the half-life. But at some point, you're going to be down to one nucleus. And after the next half-life, you're going to either still have one nucleus, or you're going to have zero nuclei. That's not quite true. Zero nuclei that are what we had before. Okay, you still have nuclei. Okay, these don't disappear after the decay. They just change into something else, right? Okay, but after a certain amount of time, you're going to be down to one of the nuclei that you had, and after the next half-life, it's either going to be zero or still one. Yep. Yep. So Travis is saying, what happens when it's all done? Like, what happens when every radioactive element has decayed and you got nothing radioactive anymore? Well, I guess in theory, Travis, that could happen, but in practice, it would be such a, astronomical amount of time that it would take for that to happen, because the reality is some things have half-lives of millions of years. But even if they don't, even if they have a half-life of 0.5 seconds, in all likelihood, since 90% of isotopes are radioactive, in all likelihood, even if it has a half-life of a half a second, when it decays, it's going to decay into something else that's radioactive. So basically, okay, the goal is for all of them to become stable. Okay, but some of them it's a pretty long chain that they have to go through to become stable, and the time that takes, astronomical. So, yeah. So again, in theory, yeah, I suppose it's possible at some point, but not really practical. All right. So what is this equation? We said it's exponential growth decay. What does big N stand for? Number of, yeah, it's the number that you have left at the end, right? So the final amount, the amount remaining. I don't want to say a number, not yet at least, but I know what you mean there, Tanner. The amount that remains after a certain amount of time, after a certain number of half-lives, the amount that remains. N sub 0 would stand for the initial amount, the amount that we start with. And of course, little n, we've already identified that. That's going to be the number of half-lives. Now, let's look at some units here. What units would we use? There's no units, by the way, for the number of half-lives, right? T over T, the units cancel, there are no units, right? You have 6 half-lives, you have 27 half-lives, okay, whatever. There's no units associated with it. But there is for amount. What units should we use for amount, do you think? Yes, good. It can kind of, Patrick said it perfectly. It can kind of be like anything, okay? It can. It can be grams. It can be kilograms. It can even be just a number. Okay, Tanner said a minute ago, n is the number of whatever. Well, it can be a number, but not necessarily a number. It's an amount which could include a number. It could be a percent. 16% remains. That could be n, right? 100% would be n0. It could be a unit called a BQ, a becquerel. A becquerel is just a rate of decay. 1 decay per second is 1 becquerel. Okay. It doesn't matter what it is. Doesn't matter what it is, as long as it indicates an amount, and as long as n has the same units. So if you're using percent, that's okay. Just make sure that they both have the same units. They're both percent. If you're using kilograms, that's okay, as long as they're both in kilograms. In the end, when you look at it, the units cancel there as well, right? So what does it matter what units you use as long as the units cancel, as long as it indicates an amount? All right, let's take a look at this short example here. It says radon-222 has a half-life of 3.82 days. That's T1/2. What percent remains after 2 weeks? This is going to be T. We're looking for, what are we looking for? N or N0? Nope. We're looking for N, the amount that remains. Looking for the amount that remains. What do we start with? 100%. N0 is going to be 100%. In the vast majority of questions involving percentages, N0 would be 100%. There are exceptions to that, but it are usually pretty clear when there is an exception to that. So let's say N is equal to N sub 0, 1/2 to the little n. Okay, that's going to be 100 times 1/2 to the, we got to find a little n. N is going to be equal to T over T 1/2. That's going to be, let's say, 14 days, 2 weeks, 14 days divided by 3.82. What does that work out to be for little n? Thank you. 3.6649 half-lives. Let's plug that in here. Now we're going to do this on the calculator because it's a little bit of a different entry than you're used to in Physics 30 here. So let's pull that up here. We're going to say 100 times 0.5. Now watch carefully. 100 times 0.5, the little hat button there. Okay, it's not times 10 to the hat button. It's just 0.5, the little caret button or the little hat button, 3.6649. Okay, that gives us our answer here. Should be 7.88. If you get a number that is bigger than what you started with, you are wrong. Because we're talking about radioactive decay, not some kind of mysterious radioactive growth. Okay, the only way you can get a number that it's correctly that's bigger than what you started with is if this number isn't 1/2. This number is a number that's bigger than 1, which isn't going to happen here, right? Because we're stuck with a half there. Yeah, Logan? What would be the significant digits for that? That's a good question, actually. Strictly speaking, it should actually be 1, shouldn't it? Because we use 2 weeks. I don't think that's what they intended, to be honest, when they did it. No, not necessarily, no. pH, did you say? It could be pH. I'm not sure about that. Yeah, I'm not sure about that. Is it? Probably because it's logarithmic. Because there's a logarithm in there. Probably. I'm not really sure about that. But, Logan, that's a good question. I wouldn't worry a whole lot about that because in the end, they're not going to give you an answer on an exam that's 7.88% and another one that's 8%, right? And if it's numeric response, they'll tell you how many digits to fill it out to. So it's a good question, but and strictly speaking, it should be 1 digit, but it's not the end of the world if you didn't catch that. I missed that until you asked the question. All right. Let's take a look at the practice problems on 814 for the next couple minutes, okay? All right, if we don't have any troubles with this, then let's move to a question that's a little bit harder. Okay, this one's not in your book. This one says the half-life of carbon-14 is 5,730 years. So that takes quite a while for half of radioactive carbon-14 to decay. How long does it take 12.5 kilograms of radioactive carbon-14 to decay into 400 grams? This is going to be N sub 0. This is going to be what we start with. This is going to be what we finish with. Now, I don't care whether we're using grams or kilograms, but let's make sure we identify that we have to have the same units. Use one or the other, grams or kilograms. We're looking for T here, right? Looking for T. Now, the only equation that I have with T in it that relates to radioactive decay is going to be N is equal to T over T 1/2, the one that doesn't appear on our data sheet. Rearrange that, we get N times T 1/2. All right, I got T 1/2, but I don't have a little n. So let's find it. Let's find a little n. Let's look at the other equation. N is equal to N sub 0, 1/2 to the little n. Uh-oh. How do you solve for a little n here? You got a couple of options here. Let me give you option number 1. Option number 1, which many people will like, and many people will go with, and many people will do correctly and be fine with. But some people won't be. Some people are going to hate it. Okay, I know I never liked logarithms when I was in high school. I don't know about you guys, but I was never a big fan of logarithms. We'll give you that method first, then we'll give you the second method that will work for you in Physics 30, but will not always work for you. Okay, down the road if you take physics course in university or something like that. Won't always work for you because it will work for you in Physics 30 because we're told in Physics 30 that we only have to perform non-logarithmic calculations. In other words, special cases where there's always another option besides logarithms. Having said that, logs are still an option if you're fine with that. Okay, if you don't like logarithms, don't worry about this, but I'll show you how to do it anyways. You just wait for the next method, though, if you're not a big fan of logs. Okay, we got n over n sub 0, 1/2 to the little n. N becomes equal to log n over n sub 0 over log 1/2, or log of 0.5. So it becomes log of n, what do we got here? Let's say 0.4 over 12.5 over log of 0.5. Okay, let's do that on the calculator here. We thought the last one looked a little strange on our calculators. This one's way worse. Let's say log of, make sure you use some brackets here, 0.4 divided by 12.5. Okay, press equals. Let's divide that by log of 0.5. And when we do that, we get 4.97. 4.97. Now, let's say 4.97 times a half-life of 5,730 years. What is it? And that's going to be years, right? We're going to round that to how many digits? 3 digits. So 2.85 times 10 to the 4 years. Sometimes you might see that written as 2.85 times 10 to the 4A. What do you think A stands for? Atom, yeah. Yeah, which is the same thing as a year. All right, what's our second option? You don't like logarithms? Use what I call the divide by 2 method. The divide by 2 method. Here's how the divide by 2 method works. Now, the divide by 2 method will only work if it's a whole number of half-lives. And that was real close to a whole number of half-lives, right? 4.97, 4.98 half-lives, whatever. Okay, it's pretty darn close to 5 half-lives. Okay, this is going to be little n, this is going to be big N. After 0 half-lives, what did I have? 12.5 kilograms. After 1 half-life, I had 6.25. After 2 half-lives, I keep dividing by 2, right? I got 3.125 kilograms. After 3 half-lives, what is that? 3.125 divided by 2. 1.5625. Okay, 4 half-lives, let's divide that one by 2. 78125. 5 half-lives. All right, we're going to stop right there because we want to get down to 0.4 kilograms. I mean, that's a tiny bit more than 0.4 kilograms, or a tiny bit less, I should say, than 0.4 kilograms, but we're pretty darn close there. It's as close as we're going to get by dividing by 2. All right, if I took that number now and I multiplied it by 5,730, okay, 5 times 5,730, what do you end up getting? 28,650. So we're going to say 2.87 times 10 to the 4 years. Okay. Slightly different number, right? Slightly different answer. That's okay. That's okay. If you got a question like this on an exam, that number 4.97 that we got would likely have been exactly 5. Would likely have worked out to be exactly 5. If it did work out to be 4.97, both of those answers would be keyed correctly. Okay? It might be a multiple choice question where it says about how many years, right? Well, then it doesn't matter which one you get because, you know, both of them are about the same. If they wanted the exact number, okay, then it would have to be a numeric response, and both of them would have to be keyed correctly. So don't worry about that. Okay? The exact curriculum objective says perform simple. I don't know I like the word simple, because if you get it wrong, I don't know what that's saying about you. Okay? But this is exactly what it says. Perform simple, non-logarithmic half-life calculations. It doesn't mean you're not allowed to use logarithms, but it does mean that you don't have to use logarithms if you're not comfortable with that. Okay? We're good there? Okay, in a few moments, I'm going to give you a worksheet to work on. But before we do that, I want to quickly go through a couple of multiple choice questions and a graph. Where's the graph? There it is. The graph. Can't see this graph all that well, at least the data points in the graph all this well. I'll trace it through here. It's going to look something like this. In fact, all radioactive decay curves will look something like this. They're all going to have the exact same shape. On the x-axis, you're normally going to see time, although occasionally you might see the letter little n, meaning the number of half-lives. Okay, usually it's going to be time though. Could be years, could be days, could be seconds, whatever's convenient. On the y-axis, it might be the mass of the substance. It could be percentage, doesn't matter. It's going to be big N. Okay, it's going to be N, big N versus time, or occasionally big N versus little n. What is this graph going to do for us? Well, the good news is we don't have to do any y equals mx plus b stuff because it's not a straight line. We don't have to do anything with it in terms of calculations because it's a logarithmic graph here, right? The analysis of this graph to do a calculation, it is possible to do, but it's difficult. So we're not going to have to do that in Physics 30. What we are going to have to do is interpret this graph in two very simple ways. We may be asked to find an amount, or we may be asked to find a time. If we want to find out how long it takes for something, okay, then you're going to go over and down and find out the time. If you want to find out how much remains after a certain amount of time, then you're going to go up and over and read off big N. So it's either going to be over and down or up and over. There's nothing else you can do with this graph besides over and down, up and over. What's probably the most common question that could be asked for this? What's the half-life of this radioactive element? What's the half-life? In other words, how long does it take for half of it to decay? Well, how much did we start with? We started with 100, right? What do we have left after a half-life, statistically? 50. Let's go over to 50, go down, and it looks to be about 2 years. Obviously, if you were asked to answer that question, there'd be more grid lines on the graph paper, so it would be easier to see, right? Okay. But the method is good there. It's about 2 years. Easy enough, right? How much remains after 5 years? What do? Up and over. How much remains after 5 years? About 20 grams. Easy enough, right? The beauty of this, the confusing thing about this is that it's not a straight line, and we're used to dealing with straight lines. We've done that a number of times. Okay, the good news is, the beauty of it is that it's easier at the level that we have to deal with it because we don't have to do any calculations with it whatsoever. All right?